Now we're going to discuss p estimation of binomial distribution. Let's try to show this on the board. So we're talking about n trials and x successes, right? Usually like this. So it's now you have an estimator like this here, x over n. This is a good estimator, because it is unbiased and has minimum variance. That's why we love it. And also another issue is if n is sufficiently large enough, x shows normal distribution. You can assume like this. Okay, normal distribution, and this makes life easier for us. And the expected value of p with a hat is 1 over n e x, and that should be 1 over n times n p, so it should be p, right? So good. And what about the variance estimate? So it is variance of this estimator should be 1 over n square variance of x, so it should be 1 over n square. The original one was npq, right? So that should be pn pq over n should be your estimated variance here, and that should be the square root of this value should be your standard error. All right, so you can put the error bounds here. So for p, error bounds are 2 pqn, and this is for Chebyshev, and and for this 1 minus alpha confidence level, and assuming that there is large n, your n is sufficiently large, your p will be plus minus z alpha 2 p times q over n, right? So you can write this comfortably and use it for estimation. And the problem here is this one is rather hard. It's hard because you need p, right? You need p here. So here, because in its definition you need p here. But the thing is, you should keep in mind that, but if your p is close to 0.5 here, like a coin toss trials or whatever, so your standard error shifts very little because they would be very close, shifts very little. So you can use p instead of the original p here. You can use this one from the sample set. I think there was this was in your textbooks as well. For p equals 0.5, your standard error would be this one as well. And if this one just deviates from 0.5 more, and it will have more deteriorating effect on your standard error as well, like 0.45, and these are just for some numbers because it's affecting. And if your p is, for example, 0.1, so this will deviate more standard error. But that's the idea about the issue here. If we want to explain this make it more clear with an example, we can refer to the example in our textbook again. We're wondering the ratio of people using a butter brand, the ratio of people using a butter brand. Like there's an interview or something, they go ahead and ask people on the street, would you use this brand as butter in your kitchen or something like this. They ask 100 people here, and suppose that this is the image of the brand here in this population of people here. Like 59 of them said yes, okay, 69 of them showed positive behavior about this brand. So we're trying to estimate P here in that population. That's what we're curious about. For this purpose, we will have our unbiased estimator, this x over n here, and that should be 59 over 100, and that should be 0.59. But with what confidence, right? That's what we're dealing with, and that would be your error range. This should be your error range for Chebyshev theorem, for example. So it should be 2 times PQ over N, and that should be your error range for Chebyshev, like covering 75% of trials here will fall within this range. If you make this calculation, the result should be this much, okay? And if we're curious about, if you want to talk about with 95% confidence interval, if we want to speak with 95% confidence, so your 1 minus alpha should be 0.95, and your alpha should be 0.5, and your alpha plus 2 should be what? 0.25, right? I mean, never rush. I told you many times, and I'm still saying this. So it means that your alpha 2, z alpha 2, and minus z alpha 2, alpha divided by 2 should be here, and these should be the areas here. This one should be 0.25 here. That's it. But if we want to use our standard distribution table here, normal distribution table here, this should be the area we will be dealing with, where it should be 0.475, right? So let's look it up from our table, readily available lovely table. Okay, that's one. So 0.475, right? Where is it? 0.475. Okay, I found you. It is 1.96, right? That's how we use our table. 1.96 is what we're seeking. So it means that this point is 1.96, and this point is minus 1.96. Perfect. So then we continue to calculate your P with a hat plus minus 1 point, and this value over PQ over N. This is your standard error, right? All right. So let's continue. We already have all of these values with us. So the calculation would be just a brief amount of time with our calculator, and we define our upper and lower limit here. So that would be your lower limit, and this should be your upper limit here. So great. So you can say that within this population, 49% to 68% of people have positive thoughts about this butter brand is your result. But with what confidence? With what confidence? 95% confidence, you say this. With 95% confidence, you say that the trials, like 95% of trials will show this probability, will fall within this range. That's how you have the p estimation of your binomial distribution as well, right? So this is an example for this, because it's a yes-no question, right? Do you like this brand? Yes, no, it's like a coin toss. That's why it's binomial. All right, that's it.